So I made this video because in our early linear algebra group sessions, the question came up, at least it came to my mind, why should we learn equations of straight lines as a part of getting to learn linear algebra? I think it's an important question. So I thought about it and I thought I would make this video to provide some answers to ourselves. So I could find four reasons why we should really brush up our equations of straight lines, and two of them are fairly general and two are specifically related to linear algebra. So let me try to articulate what I think are the reasons. So reason number one is, it's probably the light moment of this video. It's almost related to the philosophy of learning. We learn equations of straight lines because they are there, kind of like what mountaineers are known to say, that we climb mountains because they are there. Anyways, the second reason, and this is where it gets slightly pertinent, relevant, and a bit serious, is not related to linear algebra but related to geometry. So equations of straight lines and the algebraic manipulations around them. If you are studying geometry, if you are delving into geometry of straight lines, then they are a very handy tool. If you're given 10 straight lines, then your ponderables are probably, do they intersect? If they do, are they concurrent, or are some of them concurrent? Are some of them parallel? Do the non-parallel ones intersect the parallel ones in what points, etc., etc. Now you can do that graphically, but we all know that that takes a long time. It's a laborious process and becomes almost impractical. So manipulations of equations of those straight lines can get you the desired answers, can satisfy your doubts, answer your questions very easily. So those are the two general reasons, and now we come to reason 3 and reason 4, which are really related to linear algebra. And if we do this thinking, then I think it will put us in a good position to for the videos around equations of straight lines. So the third reason and the first reason why we should learn equations of straight lines as a stepping stone for learning of linear algebra. Okay, and if I can put a title to that answer, it is linear combinations. We covered linear combinations in one of the earlier group discussions, and if you remember it, then you have a set of vectors. Of course, we are talking of equal tuple vectors. It just makes sense to have equal tuple vectors in a set. So we have a set of vectors and we apply scalar multiples to each vector, which is really, we multiply each by a real number, and then these scalar multiples of that set of vectors, we add them up together, and often on the right hand side we have a resultant vector. So from a strict definition perspective, I would call a linear combination as the sum of the scalar multiples of each of a given set of vectors. That's what a linear combination is. And I said oftentimes you have a resultant vector on the right, and then in that context the questions you might be called upon to answer are how many different linear combinations of the set of given vectors yield the resultant vector. The resultant vector might be a zero vector, in which case your ponderable might be, are there multiple ways of combining the given set of vectors into a zero vector, or is there only one way? If there is only one way, then as you know, we have also touched upon this topic, we are in a situation of linear independence, and if not, then we are talking of linear dependence. That goes on to expand into the topic of what is the span of the given set of vectors, etc. Now the one thing to note is, and this is where we draw the parallel with the equation of a straight line or a system of linear equations. in that linear combination that we spoke about, the numbers in the ordered list that each vector is, right? Think of those vectors as columns, and there are numbers, we said these vectors are n tuples, so each vector has n real numbers inside it. Those numbers can go on to become the coefficients of variables in linear equations, in equations of straight lines. The scalar multiples, okay, so we are in a multiplicand multiplier situation for each vector. The scalar multiple is the multiplicand and the vector is the multiplier. So the multiplicand scalars, they can go on to become variables in a linear equation. And of course, the resultant vector on the right side will go on to become the right hand side of the system of linear equations. And last but not the least, if you have n tuple vectors, then you have n linear equations, and the better way of looking at it is, if you have m tuple vectors, then you have m linear equations, and if you have n number of vectors, then you have n variables. And the reason I spoke about m and n is because eventually this will all go towards matrices, and if you remember from high school, m by n is typically represented as the order of the matrix, but not really relevant to this video. Now, since we just demonstrated to ourselves that a linear combination of vectors can be mapped to the picture of a system of linear equations with the right hand side, which is the resultant vector, that means that the questions with regards to a linear combination that I spoke about earlier, those questions can be answered if we apply the techniques of solving linear equations. And in our group session, we really are going to be talking about equation of a straight line in the xy plane, so that we are really talking about two vectors. As I said earlier, if you have two vectors, you have two variables. Those vectors can be m tuple, that's fine. So I hope that gave us a good explanation about around the third reason, which is the first reason why, as part of linear algebra, it's good to have a backgrounder of equations of straight lines. Now we come to the fourth reason again, and this is the second reason related to linear algebra. The title of this reason is linear transformations. We have not discussed linear transformations in depth yet, and hence you'll just have to hear me out and kind of at this point of time take it as a leap of faith. A linear transformation is really a function, and we all learned functions in school and high school, right? So think of the linear transformation as a machine or a black box which takes a vector as an input, does something with it, and gives a vector as an output. To go into further depth or to further demystify it, in a linear transformation can be represented as a product in which the multiplicand is a matrix, the multiplier is the input vector we spoke about, and the product on the right hand side of the equal to sign is the result vector. That's what we have. We have a matrix, we have an input vector, and we have an output vector. Now, if you remember matrix multiplication, right? If you remember matrix multiplication, and in this case, we have a matrix which is the linear transformation, which is really m by n, and we have a vector, which means we have just one column. Okay, we have just one column. the multiplication of this matrix by the input vector, and let's make an assumption that the input vector is represented by variables, let's say x1, x2, x3 up to xn, xn, yes. That multiplication again will map on to the picture of a system of linear equations. And I am trying to explain this just the way I did it with linear combinations. What will happen is the numbers within the matrix, which is the machine or the linear transformation, will go on to become coefficients of variables in the linear equations. And the elements of the input vector, which I said we will treat it as a variable, so you will have these alphabets like x1, x2 in there. They will actually become a linear combination. They will actually form a linear combination of the column vectors of the matrix, and hence we are back to the same analogy as in reason 3. The numbers in the matrix, quickly now, the numbers in the matrix will go on to become coefficients of variables in a system of linear equations, and the alphabets within the input vector will go on to become the variables themselves of the system of linear equations. And of course, the result vector will be the right hand side of this system of linear equations. So again, in a, let's say a problem such as your linear transformation, that is, the matrix with the numbers inside, the resultant vector. So the resultant vector is expressed as actual numbers, an ordered list of numbers, and you are wondering what are the input vectors that could give this resultant vector under this linear transformation. And that's a situation where I think you are trying to find a pre-image of a linear transformation. In this case, again, since we just said, or I tried to explain, that this can get mapped to the picture of a system of linear equations, solving this kind of a problem, trying to find the pre-image of a linear transformation, can be done by using the tools and techniques available to us to solve a system of linear equations. And the tools and techniques to solve a system of linear equations, in school we just used to play the equations one against the other, arrive at the value of one of the variables, then get into back substitution. In linear algebra, we will use techniques related to matrices, we will use Gaussian elimination, we will use more sophisticated techniques which are referred to as I think Gauss-Jordan elimination techniques. We'll use the row echelon format, we'll use the reduced row echelon format, and while doing all of this, we will naturally enter the world of equations. Again, if you have a two-tuple input vector, right? In other words, if the transformation matrix has two columns, then you will be talking of equations of straight lines in the xy plane. Now I really want us to think about it, and the reason I did not whiteboard this is because I wanted to think as I spoke, so that I think we really need to, up to a point in linear algebra, maybe it's a good practice to try and visualize things. Of course, a point will come, and the whole point of linear algebra is that you shouldn't have to visualize things. That is when we make the jump from visualization to abstraction. But at an early stage, I think it's good if we try to logically think of these things. That's what I tried to do, and I hope this is a good enough backgrounder for the session that we'll have on equations of straight lines.